Hello, I'm Thomas,
And I'm Ishan.
and today we're interviewing some UNC Chapel Hill students to gauge their understanding on quantum computing. Excuse me, bro.
Yo, what's up?
Hey, do you think I could ask you a couple questions about quantum
yeah.
computing really quick?
Yeah.
Yeah, so I was just wondering, have you heard about the technology?
I mean, I feel like there were some headlines recently, but I don't really know.
Some headlines you said?
Yeah. Some
I see,
Microsoft.
so, Microsoft. So try and describe quantum computing to me. What do you think it is?
Like, is it like a really small computer? That's it.
Come on.
That's what I
Come on,
Come on, man.
Hey, how's it going? We're doing a little interview, and we wanted to ask you, what do you know about quantum computing?
Me personally, I wouldn't say I know very much. I know it has something to do with computer science. That's about it.
Quantum computing, maybe like stuff with like quantum mechanics.
Okay,
Like combining that with
What
computer
could you tell
science.
us some about it?
As you can see, there's some serious misconceptions of quantum computing, but in the future, it may have some pretty great applications.
Now, onto our project.
I'm proud to present our presentation for the 2025 Carolina Quantum Hacks, featuring hybrid, quantum, and classical machine learning for breast cancer classification. Traditional machine learning can be a very powerful approach towards classifying medical conditions based on various biomarkers. One example of this is classifying malignant and benign tumors in women diagnosed with breast cancer. In our project, we first apply a typical random forest model to a Wisconsin breast cancer dataset, attempting to find a correlation between tumor traits and the malignant/benign status of the tumor. After this is done, we apply a variational quantum classifier to the data to see if it could improve our results. Here's what we found.
This bar plot highlights the 4 key features that the random forest model used to classify tumors, 4 of them being perimeter, area, texture, and radius. By focusing on these, we achieved a higher accuracy using a more simple, faster, and interpretable model. This plot shows the distribution of confidence scores from a random forest model, where each bar represents a predicted probability for its chosen class. And the red line marks our threshold at 70%. The data points that were less than 70% would later be flagged as uncertain and ambiguous, which would later be classified into a different subset, where our quantum model would later reevaluate it. This confusion matrix shows how the quantum classifier performed on the most ambiguous cases. As we can see, it correctly identified 5 out of 6 malignant tumors and 2 out of 3 benign tumors, bringing the overall accuracy of this model to 78%. Even with a small, highly uncertain subset, the VQC still demonstrated massive predictive power over the classical model.
This breakdown shows how our hybrid approach boosts performance on low confidence predictions. While the random forest model struggled with ambiguous cases with around a 22% accuracy, the quantum VQC model improved that to 78%. By combining both models, our hybrid approach achieved an accuracy rate of 93%, highly outperforming both models by themselves. This plot shows the loss function of the VQC using the Cobila optimizer. You can see a sharp drop in the loss after the first 20 iterations, followed by a stable minimum. This shows that the quantum model successfully decided boundary decisions for the ambiguous cases that the classical model could not. This diagram shows how our QVC works. The top half shows how we encode classical data into quantum states using a series of Hadamard gates and phase gates. And the bottom half is the ansatz, which uses quantum circuits to learn about data through optimization. Thanks for tuning into our presentation.
And we hope you enjoyed our findings on quantum computing. We hope to educate more students in the future.